I have to apologize. It's going to be shorter than even usual because I've got two other classes and they both have tests this week. So I just don't have enough hands, you know. But anyways, I'll make it up to you on Friday. I'll talk twice as fast.
Yay!
Okay. All right. So last time we had continued our discussion about computing these time ordered products of operators. So, tell me when. Right there? Okay. So we had continued our discussion on computing these time ordered products of operators. And what we saw last time, or what we developed, was something called Wick's theorem. Wick's theorem tells us that when we take the time ordered product of these operators, it's the same thing as putting them in normal order, which normal order meaning all the A's to the far right, all the A daggers to the far left, right? And then plus all possible contractions. All right, so for example, we worked out the for field case, right? And so we had, we consider all possible contractions. So that's no contraction, one contraction, two contraction, on and on and on, depending on how many fields we have. And I'll show you a really complicated example in just a minute. Okay, so we have those first few terms that you still have some uncontracted fields, right? And by contraction, we saw that when we talk about contracting fields, it's really just a shorthand notation or pictorial, not really pictorial, but how would you say it?
Alternate.
Yeah, just an alternate way of writing the expression for the Feynman propagator. Okay, so when we contract two fields, what we're basically saying is that we're creating a particle, say in spacetime at point x1, and we're propagating it to spacetime point x2, and then we annihilate it. Hold on, let me test my wife real quick. She's just going to keep writing. Should just have one of those automatic buttons that says leave me alone. Oh crap, this is recorded. I have to go back and edit. That's all right. She doesn't watch these QFT lectures, so it's all right.
You're safe.
Yeah. So the nice thing about Wick's theorem is that
Email it to her. Yeah. Oh, blackmail.
Yeah. Automatic fail. No, she's used to it. No, it wouldn't even phase her. So we see, like in this Wick's theorem, that the nice thing is that when we apply it, what we end up with are terms that have uncontracted fields, and then terms that are fully contracted. And any terms that don't have or that have uncontracted fields will give us a zero vacuum expectation value, right? So when we sandwich those between the vacuum kets, between the vacuum ket and vacuum bra, they're going to vanish. They're going to give us a zero contribution. So Wick's theorem is telling us that when we consider VEVs, we only have to consider the fully contracted terms. So in this case, the last three pieces. Right? And those three terms, if we use this rule, if you will, would give us the time ordered product of four operators in terms of pairings between, or pairings of Feynman propagators between all the space-time points, right? So we just have to consider all the possible full contractions. All right, and then we also talked about trying to simplify this analysis a little bit and not work explicitly with these expressions, but to try to come up with a way to work these guys out diagrammatically. Right? So if consider this case right here, right? Like I said, we're here. This is creating a particle at x1 and propagating it to x2, right? And this one starts at x3 and ends at x4. So that would be this first diagram, and then we'd have the second term, and then finally the third term. Okay. So that was it for non-interacting theory. And then what we did last time was to start to consider the case of adding back in our interactions. Right? And that's when things get interesting. Okay. And so the way we do this is, remember, we want to take a Taylor expansion, basically, of this this operator, these interactions. Okay. And so, for example, we would have this first term. So this is for the propagator. Okay. So this is for the time-ordered product two operators. First, we have the propagator, right? And then we're going to have what we would call the first-order corrections. Okay. And those first-order corrections depend on what the interaction Hamiltonian looks like. And for the case of phi to the fourth theory, we would write down something like this. Okay, so we want the time-ordered product of 6 fields with this integration coming in from the vertex. Okay, the vertex. Okay, for the interaction, I should say the interaction at this point. Okay, and what we did was we considered the possible contractions, right? We found that there were 3 ways that you could contract x with y, and then the 3 various ways you can contract the z fields amongst themselves. Or you could consider contracting phi x with phi z, and then phi y with phi z, and it turns out that there's 12 ways of doing that. Right? So you have to count up all the different ways that you can contract these fields. But in the end, you can just, once you have the contractions, you can write down the Feynman propagators for those contractions. Okay? And notice that this is coming in order lambda, so that would be our first order correction. Okay, so if you use this diagrammatic way of thinking about these amplitudes, you would say that this first term would correspond to a particle being created at x, propagated to y. And then you have 2 propagators that both start and end on spacetime point z. Right? So they would form this kind of infinity, whatever you want to call it. It looks like an 8.
Mo piece.
Yeah, okay. But even though, so even though these are separated diagrams, they're considered one diagram as far as our expansion goes. And then this other term would have a particle created at x, propagated to z, another one say created at y, propagated to z, and then one propagator that goes from z to z. Okay, so that would look something like this. Right? Okay, so that's where basically we stop. And what I want to do is kind of carry this on and see if we can generalize our diagrammatic approach a little more. Okay. All right, so let's consider the lambda to the cubed power. Okay, so this is going to involve 3 vertices. Okay, and it's going to so this is the correction of the propagator. So it's going to involve 4, 8, 12, 14 fields. Okay, and what we want to do is contract those guys. So you can see that this 1 over 3 factorial is coming from the Taylor expansion, right? And you got 3 factors of the vertex factor. Okay. All right. So let's consider just one possible pairing configuration. All right. And you're going to see that it's enough. You don't want to do anymore. Okay. So this is one possible way of pairing these guys up. Okay. And you can see here, so here I've got 3 different vertices, one at z, w, and u. And this is just one particular choice. So I'm taking phi x with one of the z's, phi y with one of the w's. And then from there, I'm contracting all the whatever's left over in those vertices with each other. All right? So if we apply Wick's theorem, then we can write this, this what I call it, the contraction configuration, in terms of Feynman propagators. All right, so we would have, again, the factors from the Taylor expansion, we've got the three integrals over the vertices, and then we just write down the propagators for each of these contractions, right? So here's the x, z guy, this guy. There's the y, w, right, and so on and so forth. Okay. So you can see that this, complicated term, involving 14 fields, we can write down in terms of 1, 2, 3, 4, 5, 7 propagators, right? Okay. Now, it turns out that, as you probably guessed, there's a number of different contractions that would give the same result. All right, so we could, once we contract x with one of the z's and y with one of the w's, then there are a bunch of contractions that can be mixed up that will give us the same result. Okay, and so here's how you count. Okay, just for this particular diagram. Okay, so there's we have three vertices, right? So that we have 3 factorial ways that we could interchange the vertices, right? When we write down these terms. Placement of contractions on the z vertex. So on the z vertex, right, we're contracting one of those with our external field. So there's 4 times 3, so it's basically, so it's 4. We have 4 possible ways that we contract one field, and then 3 possible ways that we can track the other one. In the W, so in the W case, we end up with 4 times 3 times 2 ways of contracting these vertices. In the U case, we have basically 4 times 3 again. And then we have to account for the fact that the W and U guys, we can interchange those two, right? To interchange those contractions with themselves and the outer fields. And if you do crunch all these numbers, you find out that there's 10,368 possible contractions just for this one term, okay? And that's only 1/13 of the 135,135 possible full contractions, right? So starting with this guy, right, and figuring out all possible contractions, there's over 135,000 of them, okay?
That's the next one.
Huh?
That'll be the next one.
That's the next one. Yeah. Nah, that'll be the final. Right? But the thing you notice is no matter how I contract them, well, for this one particular term, right? The one that has 10,368 contractions, they all would have the same diagrammatic representation, right? So if you do all the same contractions, but in different ways, you're still going to end up with this string of Feynman propagators, right? And if I draw the diagram that corresponds to that string of Feynman propagators, it would look something like this. Okay, Peskin called it a cactus diagram, but it looks more to me like a bowling diagram, right? Like a bowling pin and bowling ball. I don't know. Anyways, but he calls this the cactus diagram. Okay, and this one diagram would represent those over 10,000 contractions. Okay, so it's hopefully it's obvious to you guys that the way we want to go is to write down the diagram for a particular process, and then figure out from the diagram what the amplitude is in terms of Feynman propagators or vertices, right? Okay, so that's what our approach is going to be. Okay, so we're going to let this one diagram represent those over 10,000 identical terms. Okay, and this is what we do in practice. So we always, if I said compute the whatever correction to the whatever correlation function or time work product operators, the first thing you would do is you would write down the Feynman diagrams. Okay, and then from those Feynman diagrams, you'll apply some rules to figure out what the amplitude is. Okay? The tricky part, though, is going from the diagram to the terms, right? Because here we have one diagram, and it represents over 10,000 possible terms, right? So that's the tricky part, is going from the diagram to the actual amplitude, because you have to try to figure out what that overall constant is, okay? And that's where the so-called Feynman rules come out, right? So what we could do is we could follow the same process that we did above, right? So for every vertex, we throw in a factor of the coupling over 4 factorial and then integrate over that space-time point. We could put in the 1 over n factorial for whatever term in the Taylor expansion that we're doing. And then we can compute the combinatorics by considering all possible contractions, like what we did here. Okay? But you notice a few things right off the bat. One is that we have this factor of n factorial that comes in from interchanging the vertices, right? And that term is almost always going to cancel the 1 over n factorial from the Taylor expansion. All right, so we can forget about that. We can forget about that term, this part of the rules, if you will, right? And then because we have a 4-point vertex, when we go to contract those things, the legs of the vertex with other lines, there's 4 factorial ways of doing that. Okay, there's 4 factorial ways of arranging those fields on the line. Okay, and that is going to cancel this 1 over 4 factorial that we wrote down for the vertex of this guy, right? And that was on purpose, right? So we put that 4 factorial in because of, we didn't know in the beginning, but let's say we did, all right? That we guessed that there was going to be 4 factorial ways, all right? So we just put in this factor by hand, and so that it will cancel off this combinatoric 4 factorial, okay? So we can, reduce the Feynman rule, or the rule for the vertex, to be just coupling times, this integration. Okay? All right. Okay, so if you did that, right, if we do that, we write down the diagram, we figure out the combinatorics, all that stuff. Unfortunately, there's still some overcounting involved. All right, so when we write down the diagram and we apply that procedure, we're still going to be overcounting. Okay, and that's due to symmetries of your diagram. Okay, and I don't want to get bogged down in this. I know we did in the summer, and every QFT class it seems like I teach, people get bogged down with symmetry factors. Okay. And there's just no point in getting bogged down in them, because you will not run into them in your life, even if you're, unless you're computing multi-loop corrections to some process, which only a few people in the world actually do. You'll never really have to worry about symmetry factors. Okay, but let me just in general discuss them. Okay, so. For our particular diagram, the cactus diagram, or the bowling alley diagram, we would have actually an overcounting factor of 8. Okay, and this 8, this number, is what we call the symmetry factor. Okay, and so the 8 is made up of 3 factors of 2. Okay, so these 2 factors, the first 2 factors of 2, come from lines that start and end on the same vertex. Right, so they come from this guy and this guy. Why are they factors of 2? Because I can imagine, cutting, that loop right there, and then flipping the propagator, right? This propagator that completes this thing, right here and here. And so I have 2 possible ways that I can do that. Okay? So that gives me these 2 factors of 2. And the last factor of 2 are from 2 propagators that connect W to U, right? So these guys, this guy right here and this guy right here. Because I could cut those, cut them off and switch them, right? And put them in the opposite place, and I would still get the same diagram. Okay? And we haven't accounted for that in our procedure, the way we've done things. Okay? So the way you view these things is that for these two symmetry factors, the ones that involve these closed loops, The diagram is symmetric on an interchange of the two ends of the line. That's exactly what I said. That, you know, if I cut those lines there and flip them, I'll end up with the same expression. And here, again, the diagram is symmetric on the end of the interchange of these two propagators, okay, on the left and right side. Okay, and another possible source of overcounting that we don't necessarily see in this guy is when we have what are called equivalent vertices. So that would be like the case of, well, I don't really have an example off the top of my head, but that I can state. But I'll show you an example when we get to a theory besides 5 to the 4th. Okay. But anyway, so those are possible. So interchanges of propagators and what are called equivalent vertices, or vertices that you can interchange, and they wouldn't change the structure of the diagram and/or change the amplitude. Okay, and so what we have to do is to get the correct overall constant. So we go through the same procedure that we said before. So we write down the diagram. We figure out. We figure out the combinatorics. We use the rule for the vertex, and so on and so forth, right? And then we divide by the symmetry factor, right? Whatever the symmetry factor is of the particular diagram. So in this case, we would divide by 8. Okay, and in that case, we would have fully accounted for any overcounting, and we'd be safe in writing down the amplitude for this diagram, and it would represent those 10,000 and whatever possible contractions that we had when we were working with those field expressions. Okay? The good news is, like I said, you'll never, ever, ever, ever have to evaluate a symmetry factor greater than 2. Okay, I mean, like I said, there's only, diagrams like this, if they came up in real life, there's only a few people in the world that would know how to compute these things, okay? Because they're multi-loop diagrams, and we'll see that, you guys know that computing one loop is hard enough, okay? And it's typically, it is enough, when you're doing things in perturbation theory. Loops come in at higher orders, and so this is, this would be like
this is lambda 3, so
yeah, so this would be like the
next
to leading order term, right? Okay. So anyways, so you never have to do that. And in fact, these are the two diagrams that we'll run into this semester that we'll have to compute symmetry factors for. And the symmetry factor for both of them is just 2. Okay, so this guy, we've already seen, it comes in at 5 to the 4th theory, right? And the symmetry factor comes from the fact that I can cut this propagator here and flip the ends, right? And then this guy is like the second factor, where I can cut these propagators here and flip-flop them, okay? So the symmetry factors, like I said, people get, if you're reading a QFT book, there's usually a lot of time spent on them. Like in the Shrednicki book, you look, there's like 5 or 6 pages on symmetry factors, and then you never use them again in your life, okay? So just beware, okay, and don't get bogged down in it, because it can fry your brain, if you try to think about it too long, all right? Okay, so we're finally in a position now to write down our Feynman rules, okay? So what we would have done is, in real life, we would have computed a bunch of these things, right? We would have computed, a bunch of these different terms. Hopefully, we would start out at lambda cubed. We'd start at something easier, but we would compute these things. We might compute maybe 4-point functions, not just 2-point functions, and we would start to notice this pattern, right? We would start to notice that I can get the same amplitudes, right? If I follow these rules. If I first write down the diagram, use the rule, the procedure that we have for calculating the overall factor, right? And then dividing by the symmetry factor, right? So for each propagate, so the rules go like this, okay? So these are the Feynman rules for phi to the fourth theory. So for each propagator, we write down a Feynman propagator. Right? So this is going from the diagram to writing down an amplitude. For each vertex, write down the factor of the vertex and then this integration. And then for each external point of your diagram, so in our 2-point function, we have 2 of those, you just write down 1. Okay? And you don't even have to write down 1, because 1 times anything is anything. All right? And then you divide by the symmetry factor. Okay? And those are the rules that if I gave you, this diagram, or if I even piled more loops on top of these things, you'd be able to write down the amplitude for it in a couple lines, right? Which is pretty damn amazing, if you ask me. Okay. All right. Okay. So these are, you can tell by looking at the propagator, these are in position space, right? And it turns out that most of the time it's a lot easier to work in momentum space. Okay? And we'll see examples of that later. Okay, but this is how. So these are the position space Feynman rules, and these are never used. You never use these. Okay, you're always working with momentum space. Okay, so and I'll show you why in just a second. Okay, so what we want to do is work in momentum space, and the way we do that is to work with the Fourier expansion of of the propagators, right? So in other words, writing these propagators like this, okay? Right, the way that we've learned how to write them, okay? And then what we want to do is, in diagrams, we want to on our legs, right? On these legs, these diagrams, we want to represent kind of the flow of momentum. Okay, so this is one particular. So just consider this to be the 4-point function or 4-point time-ordered product operator or something. Okay, in momentum space, we would represent these as some vertex. Okay, and then we have these external lines, and we assign momentum to these guys, whatever momentum we want. Okay. So here I'm taking, and we indicate with the arrow which direction the momentum is flowing. Okay. So here I've got P1, P2, and P3 all incoming. They're all flowing into the vertex. And then P4 is going out of the vertex. Okay. And so what I would do is, if I was to take our Feynman rule for the vertex, which would be this thing, right? Just this, but I should have the factor of the coupling out here. But this is what it is. So I'm taking basically the Fourier transform of this vertex. Okay? And so I'm plugging in my these 4 factors, the E, the I, P, X factors that come in from the Fourier transform. And notice that P1, P2, P3 are positive, and P4 is negative, so it gives me a plus sign here. But this integral, we all know what it is. It's just an integral representation of the Dirac delta function. Okay? So when we go from position space to momentum space, where we would write down a diagram like this, the vertex basically boils down to a Dirac delta function. Okay? And that simplifies our lives because in diagrams, we're also going to have these guys, right? Propagators floating around. Okay? So we're going to have these integrations over momentum. Right? But with these Dirac delta functions, they're going to allow us to get rid of a lot of these integrations. Okay? And just a side note, this delta function is telling me that I have to conserve 4 momentum. All right, so it's a 4-dimensional Dirac delta function, and you can see that P4 has to be equal to P1 plus P2 plus P3. And like I said, these delta functions are useful. So this is the reason why you want to make that switch to momentum space is because vertices become delta functions, and delta functions let you evaluate integrations over propagators. Okay. Right. So in momentum space, our Feynman rules become this. So for each propagator, I introduce a factor of I over p squared minus m squared plus this I epsilon piece. And then for each vertex, we write down a vertex, we have to indicate the flow of momentum, but we just assign a factor of minus I lambda, right? Because we've done the integration that was there in position space using our Fourier transforms. Right? And then for each external point, we have to add in a factor of the e to the IPX from Fourier transforms. Okay? And we'll see that these eventually will go away when we start to compute observables. Okay, so those are our rules for the pieces of the diagram. And then there are a few more rules, right? So one is we have to impose momentum conservation at each vertex. Okay, so what you would do is you would write down. So if I had, I got a pen.
I've got it.
Just let me borrow it for just a second. Thanks. So let's say, I told you to compute the 4-point function. Now let's say, so let's say I said compute one of the corrections to the 4-point function.
It's off the screen.
Right? And in phi to the 4th theory, so the only thing I can really do is put a loop here. This, okay? So I would write down the diagram, okay, and I would assign some momentum. So we put P1 here, P2 here, and then P3 here, and P4 here. Okay, so my Feynman rules so far tell me that for each external point, where'd they go?
All the momentum is incoming.
Yeah, you can assign the momentum any way you want. Okay, the external momentum any way you want. So I'm choosing to put them all inward. Okay. Well, for our external points, I've drawn the momentum coming in. So what we would do is we would assign 4 factors of e to the IP x's, right? So I'd have like e to the IP1 dot px1, e to the IP2 dot x2, e to the IP3 dot x3, and then e to the IP4 dot x4. Okay, so those would be my 4 external factors. And then here for each propagator, right? When I'm talking about our internal propagators, okay, so for each propagator would be this internal propagator.
You're the highest.
Okay, yeah.
Okay, so you would have some factor for the propagator, okay, but you had to conserve momentum, right, at these vertices. So this one wouldn't be that bad, right? But because this is just P1 here. But here we would have an undetermined momentum, right? It's undetermined because if you write this diagram down in position space, and then you do your Fourier transforms, you find out that you don't have enough delta functions to kill off all the integrations. Okay, so
Thank you.
so you're left with one integral that you have to perform. Okay, and so in general, when you write down diagrams and you have loops, you're going to have that undetermined momentum. And quantum mechanics tells us that we have to sum over all possibilities of that values of that momentum. Okay, so if you have loops, you'll have integrations left over. Okay, but if you don't have loops, there's no integrations left. Okay, and then finally we divide by the symmetry factor. Okay. All right, so let me just compare. Okay, so here again, position space, we never use them. Momentum space. Okay, this is what we'll use for internal propagators, vertices, and external points. Okay, and these will get modified a little bit, like I said, because the external points we're going to see when you're computing observables, they can just write them as one. Okay. All right. I'm almost done actually. Yeah. Okay. Yeah, so we're almost done with the calculation of the correlation functions, or at least we have now a prescription for calculating these things, okay? However, we have to account for one thing that I've kind of swept under the rug, right? And that was this weird thing that we did by taking t to infinity, but in a slightly skewed way,
What
okay?
was for again
The taking that limit?
the for the finding or
Oh, imposed momentum conservation.
yeah.
Sorry. Right. Right. Remember, we had to do this to ensure that we were working with the non-interacting vacuum states. Right. Is that why we did that?
There was a pole in the denominator,
Hold.
and we have to impose this I epsilon to go around the pole.
Is that what we did it for?
Well,
No, that's what we did in the summer, and that's what I'm about to talk about. We did it. Shoot. It's related. I know it's related to. Somebody had to go back and notes and look. I don't even know. This is basically a wick rotation, but it was.
we're asking why did we do it in the first place?
Yeah, why do we do it in this case? I don't remember. Anybody? It's okay. It'll come back to me. All right. So what we had to do is we had to put this back in. It was there, and then somewhere along the way, I kind of dropped it, and none of you guys noticed. Okay, so y'all get 10 points taken off for today. But so we want to put it back in, right? So at some point we had it in our calculation of the correlation function. Okay, so what we want to do is go back there and plug it in, and the place to do it is this is page 8. This is page 7. The place to do it is going back to this guy. Right? So in momentum space, we want to go back and put the limits in here. For t goes to plus or minus infinity times this 1 minus I epsilon piece. And so that's what I'm doing here. Right? So I see I've separated out the time integral from the spatial integral, and I've still got this exponential thing here. Okay? And what you notice is that this exponential, this guy, is going to blow up, right, as z goes to plus or minus infinity, unless the momentum, what was I going to say? Oh, unless the momentum has an imaginary piece as well, or an imaginary piece as well, so that the whole argument of this thing is imaginary, right? Because if the argument's imaginary, I guess I'm talking about the p dot x's, then I'm going to get something damped, right? A damped exponential, okay? So it won't blow up. And the way we achieve this is by skewing the time part of the form momentum. In other words, the energy component, right? So we skew this guy by some 1 plus epsilon, I epsilon piece. Okay? And this is what Michael was talking about. This should sound familiar because it's exactly what we had to do when we were computing the Feynman propagator back months ago, right? When we had the poles that we had to somehow deal with, right? And so what we did was we skewed, we did a wave rotation, right, of the momentum or the energy part of the integral slightly into the complex plane, right? And so by doing that, we kind of solved two problems. We were able to compute the Feynman propagator, but now it allows us to deal with this this weird limit thing of taking t to plus or minus infinity. Okay, or so it appears. Okay, so it appears that in most of these diagrams that we'll encounter will be okay. All right, but there are certain classes of diagrams. It's a cliffhanger until next week. There are certain classes of diagrams where this doesn't save us. Okay, where we end up with infinities basically. So we have to deal with those somehow, all right? So we'll do that next time. Oh, I forgot, Friday, not next week. So you don't have to wait as long, right? So we'll deal with this on Friday, and then we'll start to compute cross sections and scattering amplitudes and stuff like that. All right? Okay. Any questions? No? Okay. All right, so we'll see you guys Friday at 2:00 here.
Okay.
Okay? All right.
Thank you.
All right, see you guys.
Bye. Okay. Tuesday for
No, I do in my office, so. Yeah, is that the homework?
Yeah.
Okay. Sean, no Lake Tech this time, man?
Yeah,